Hi, welcome to the first video on my proof by induction inequality series. So in previous proof by induction videos, we saw that we would first consider a base case, we'd then assume for n equals k, and then we would consider. Now this is exactly the same, except we're going to do the base case, we're going to assume like normal, but when we consider, we have more choice in what side we pick, which we'll sort of see later. We're not going to write the target as always, except we don't really write the target when we're considering the divisibility case. And then after that, we're going to use the assumption to create the inequality from the consider. And we're going to use the target to create an easier inequality to prove. Usually this will be just some simple straight away you can prove it, or it will be something more complicated such as a quadratic inequality. But usually it's going to be something we can do with other techniques. So let's begin. So prove that n factorial is bigger than 2n. So this is something you can kind of expect would happen. For 2 factorial, we're going to have 2, and then we're going to be timesing by 3 for the next step, and then we're going to be timesing by 2 squared, 4. So clearly at that point, we're going to be getting a number that's bigger than 2n. And then after that, we're going to be timesing by a number that's bigger than 2 each time. So clearly this side's going to be getting much bigger than this side. So we'll do our base case. So this case, in this example, we start with n equals 4. So base case, n equals 4. We have 4 factorial is equal to 24. On the other hand, 2 to the power of 4 is equal to 16. So clearly true for base case. Next, we're going to go to our assumption step. So for our assumption step, we're going to assume that it's true for n equals k, where k is an integer. I.e. we have that k factorial is bigger than 2 to k. We then go on to our consider. So consider n equals k plus 1. So this time I'm going to consider just the left side to keep it simple. So k plus 1 factorial. We then want to somehow involve our assumption. So I want to involve k factorial here. Using a little trick with factorials, this is the same as k plus 1 times k factorial. So I can make this smaller by replacing the k factorial with a 2k. So we get to this stage. Now this is where it's a good sort of idea to write our target down. Our target is to show that k plus 1 factorial is bigger than 2 to the k plus 1. So what we want here is we want a 2k plus 1. But what we have is a k plus 1 times 2k. So what I want to show is, I want to show that k plus 1, 2k, is bigger than or equal to 2 to k plus 1. Now on both sides I can divide through by 2 to k. You might have seen this trick previously. 2 to k plus 1 is the same as 2 times 2 to k. So we want to prove that k plus 1 is bigger or equal to 2. But n is bigger or equal to 4, so k is bigger or equal to 4. So this here, actually, we get that k plus 1 is bigger or equal to 5, which is bigger or equal to 2. So we prove it. So what we get is that this is bigger than or equal to 2 times 2 to the k, which is equal to 2 to k plus 1. Now we're done. We've shown that k plus 1 factorial is bigger than this. So our first step, we try to involve our assumption. So we split the factorial up. We then used the assumption. We then compared what we have with our target. So I want a 2k plus 1, but I've got a k plus 1 times 2 to k. So I need this thing well, I already have this thing, sorry, in my target. So I need this thing to become a 2. And then we've got exactly what we want. So finally, we make our conclusion. So as true, for n equals k plus 1, when true for n equals k, and true for base case, n equals 4, by mathematical induction, I'm just going to put math induction, but you should probably write it all out. It must be true for all n greater than or equal to 4. And that's all there is to it. This example is quite easy because, well, our inequality was quite simple. We just had to show that k plus 1 is greater than or equal to 2. In other examples that we're going to see, we're going to have to show a quadratic inequality. And I'll see if I can find some a lot more complicated cases to show. But the main thing is, with proof by induction, we're trying to prove a hard inequality by reducing it down to an easier inequality, like we sort of done in this case here. But thanks for watching. In the next video, we'll have a look at a more tricky example.